Hi, who is online? Hi, hi, hi. Good evening, class. Who is online? Destiny, hi. Is that you and Destiny? You're welcome. Is that you and Destiny? You're welcome to today's class. Jagwa, you're welcome. Okay, Chiyo Destiny, you're welcome. Okora from Maria, you're welcome. You're welcome to today's class. Someone of Grace, you're welcome. Okay, it's Claire, you're welcome. Claire, you're welcome. I didn't see your sister in SS2 class. Why? Rosemary, you're welcome. Is that Chimene? You're welcome to today's class. Repro Health One, you're welcome. Thank you for stopping by. Jessica Mbanude, you are here. Welcome. All right, let's dive into what we have today, which is what? Radioactivity. Victory, you're welcome. Hi. Okay, let's write what is on the board so we can proceed. Please, if you are just joining us, please give it a thumbs up. Give it a thumbs up, okay? All right. So let me explain. Radioactivity. Radioactivity. Radioactivity is the spontaneous decay or disintegration of the nucleus of the atom of an element. Is the spontaneous decay of the nucleus of an atom of an element, during which it emits alpha particles, beta particles, or what? Gamma rays, or a combination of any or all the three, and energy. Let me explain it again. Radioactivity is the spontaneous decay or what? Disintegration. The spontaneous decay or disintegration. What is this spontaneous decay? It means that these elements that are said to be radioactive elements, they decay spontaneously from their nucleus. Decaying spontaneously means they decay naturally on their own. Okay? They decay naturally on their own. And as they decay, they emit particles. Either they emit alpha particles, or they emit beta particles, or even what? Gamma ray. And there's a situation whereby an element can emit alpha and beta. That is what I mean by the combination of any or all the three. And even an element can also emit alpha, beta, and gamma at the same time. And it must emit heat or energy. So that is the process of what? Radioactivity. It's not ordinary element that can emit radiation from their nucleus. It must be a radioactive element. So radioactive elements are those elements that spontaneously emit radiation from their nucleus. They spontaneously emit radiation from their nucleus. So these elements are configured naturally that they can decay on their own from the nucleus. Do we understand? All right, so that is radioactivity, and it's only radioactive element that can exhibit this concept of radioactivity. Examples of radioactive elements, I have what? Radium, thorium, ionium, polonium. I still have what? Uranium. I can add uranium. Uranium is also an example of a radioactive element. It can emit radiation spontaneously from their what? From their nucleus. All right. Hello, you're welcome. Please, do you understand what I explained? If you are just joining us, give it a thumbs up and make sure you subscribe to this channel. Do we understand the explanation of radioactivity and radioactive element? Jessica, Chioye, Maria, Tamuna. Okay, understood. All right. Are we done writing? Are we done writing? Okay, please copy what you have on the board. Bere, you're welcome. How are you? Okay, are we done writing? Let's explain. Okay, we are done. Okay, let's explain. All right, the phenomenon of radioactivity was discovered in 1896, okay? the phenomenon of radioactivity was discovered in 1896 by a French physicist called Henry Becquerel. Henry Becquerel. This name is very, very what? Important for JAMB questions, okay? And I gave this question on in my community tab, okay? So you can go and check it out. Now, this was the first man that discovered this phenomenon of radioactivity when he was performing an experiment with a random sample. Now, he brought a random sample and now shielded it with a lead block. Why did he shield it with a lead block? He shielded with a lead block so that the radiation cannot do what? Escape, okay? So because the lead block cannot allow radiation to penetrate to it because it's a concrete. All right. So he now brought a photographic plate. This is a photographic plate where images form. And he now realized that in the course of his experiments with radium sample, which is also an example of a radioactive element, he now saw that we have three types of radiation. The radiation was deflected what? Slightly towards the south pole, okay? And one went towards what? Towards the north pole, and another one went straight and shows no deflection. He now concluded and said that we have three types of what? Radiation. The first one is alpha particles, the second one is beta particles, and the third one is what? Gamma ray. So he's trying to say that a radioactive element is possible that it's going to emit an alpha particles, a beta particle, and what? Gamma ray. Is that okay? All right. So look at it. Alpha particles are positively charged, so they can be attracted by the south pole of a magnetic field, and south pole, they are negatively charged. So this positive can attract what? Negative, okay? So look at these beta particles. They are negatively charged, but it is being attracted by the north pole of a magnetic field, right? So in the nutshell, for me to do a recap, I'm saying that a man called Henry Becquerel was the first person that discovered the phenomenon of radioactivity when he stumbled into an experiment with random sample, okay? Then during his course of experiment, he now observed and concluded that we have three types of radiation. We have alpha particles, we have beta particles, and gamma ray. Is that clear? All right. Vijaya, you're welcome. Thank you for coming by. Thank you for stopping. I really appreciate. All right, class, are we done writing? If you are just coming, give it a thumbs up. Give it a thumbs up, okay? Are we done? Proceed, okay? Destiny, Jessica done. Maria done. So we can proceed. Okay, so let me proceed. can say types of radiation. Radiation are the particles emitted. Okay, that is the alpha, beta, and gamma. They are radiations. Okay. So let me say types of radiation. Okay, let me say radiated particles so that I don't get. Okay, is it better now? All right, copy fast. Let's explain. Bright, you're done. Terminal done. All right, let me explain. We have types of radiation or types of radiated particles. Okay. Now, the first one is alpha particles. Alpha particles, they are helium nuclei. Helium nuclei. Okay. That is the first thing you must know about alpha particles and the symbol. And the nature of it is what? Each helium, He, each has a mass number of 4, atomic number of what? 2. They are positively what? Charged. they are positively charged. They are relatively massive, okay? So they are weighty. They are slightly deflected in a magnetic field. I've already shown you how it was deflected in a magnetic field, okay? They cause heavy ionization. They have little penetrating power. These are the properties of alpha what? Particles. Properties of alpha particles. But the one I'm going to tell you to concentrate more is the nature of alpha particle. Alpha particle is a helium nuclei that has a mass number of what? Atomic number of what? 2. Okay? And they are what? They are positively charged. They are what? They are positively charged. Because they are positively charged, they are slightly deflected in a magnetic field. In what? In the south pole of the magnetic field. Okay? So these are the properties of alpha particle. So let's go into beta particle. All right. Okay, so I forgot to add that they travel at 5 to 7% of speed of light. Okay, they travel at 5 to 7% of the speed of light. Now you know that the speed of light is constant. Most of this radiation, they travel with the speed of light, okay? Because they are still under what? Radiation. I can say electromagnetic radiation, okay? Now, the speed of light is constant and is given by 3 times 10 raised to the power of 8 meters per what? Second. This is the speed of light, okay? So for alpha particles, they travel with range of 5 to 7% of the speed of light, okay? Yes, Ocha, you're welcome. It cannot be deflected at the North Pole in a magnetic field. Why? Is because they are positively charged. And North Pole is positive. So positive cannot go to positive. Do you understand it now? Positive cannot go to positive because they are positive. So they need to go to what? The South Pole, because South Pole are negatively charged. Okay? So alpha particles need to go to the South Pole so that they can attract. So that attraction is going to take place. You see better now? John, you say you don't understand. Okay? Okay, I said that alpha particles, they are helium nuclei. So if you want to write alpha particle, that is helium, which has a mass number of 4, atomic number of what? 2. And they are positively what? Positively charged. And because they are positively charged, they will be deflected in what? In the south pole of the magnetic field. Because south pole is negatively charged. And alpha particle is positively charged. So you need to deflect to the south pole of the magnetic field. Okay? You understand? So the attraction will take place. All right. Now we can proceed. Let's go to beta particles. Okay, show your copy. Copy what you have on the board. Okay, are we done? Okay, let me explain. Beta particles. This is symbol for beta, okay? They are high energy electrons. They travel at approximate speed of light. They are negatively charged. They are relatively light and they have a good penetrating power. They are reflected towards the north pole of the magnetic field. You know why they are reflected towards the north pole of the magnetic field? Because they are what? Because they are negatively charged, okay? So they need to reflect towards the north pole so the attraction can take place, right? Okay, now the nature is this. It is represented by E, which has a mass number of what? 0. Atomic number of what? -1. Is that okay? It has a mass number of what? 0. Atomic number of what? -1. All right? Okay. Are we done? E means electron, okay? E is electron because they are high energy electrons. So once you see E in any equation, in any radioactive equation, E means electron, and beta particles are what? Electrons. Okay, this is even a jamb question. Beta particles are high energy what? Electrons. Do you understand? Okay, so because they are electrons, they are negatively charged, and they must be attracted by the north pole of the magnetic field, because north pole are usually positive charge. Okay, so that before attraction can take place, both of them will do what? We attract. Do you understand? Okay. Are we done? Are we done? Okay, the nature of this beta particle is this. That is E, helium nuclide. That is E, electron, okay? It has a mass number of what? 0. Atomic number of -1. All right, let's move into gamma rays. All right, can we copy? Are we done, please? Are we done? Are we done? Are we done? Jessica, are we there? Grace? Right? Maria, are we done? We are just coming double tap. Give it a thumbs up. Are we done? Are we done, class? Let me explain. Okay, gamma rays. This is the symbol for gamma ray. This is gamma. Okay, they are electromagnetic waves of very short wavelength. Their wavelength is very, very what? Short. Okay, they travel at the speed of light. Okay, they are electrically neutral, meaning they are not positive, they are not what? Negative. They show no deflection. They have high penetrating power. All right, so gamma rays shows high penetrating power and shows no deflection. Okay, then they travel with the speed of light. They travel with the speed of light, so it's very, very what? Fast. All right, so it has a mass number of 0, atomic number of what? 0. So let me just write the nature of gamma rays. This is the nature of gamma ray. It has a mass number of 0, an atomic number of what? 0. So these are the three types of radiation gotten from a reactive element. The first one is alpha particles, beta particles, and gamma ray. I hope it's clear. Right. All right, are we done? Are we done, please? Half-life and decay constant. Okay, so let's define it. All right, are we there? Are we done writing? Okay, let's go. This is half-life. Half-life, the symbol is T, base half, okay? Some still use it as normal capital T, but I prefer using it as T base half. Of a radioactive element is the time taken for half of the atoms initially present in the element to decay. That is half-life. Half-life is the time taken for half of the atoms initially present in the element to do what? Decay. For example, if the mass of the atoms in a particular element is 20 grams, and the half-life is 4 years, it means that after 4 years, this mass is going to decay to half of its original. Remember that this is the original number of atoms before it started decaying. It started undergoing radioactive decay, okay? So after 4 years, the mass is going to reduce to half of its original value. That is what? M naught over what? 2, right? And that is 20 over 2 to give me what? 10 grams, okay? Then after another 4 years, I'm going to have what? M naught over what? 4, right? Why this one will be what? 5 grams. So this is what half-life is all about, okay? That is the time taken for it to decay to its original value. So here, the half-life for this element is 4 years. So after 4 years, it decays to half of its original value. It keeps decaying until it goes down to nothing. And as time increases, the number of atoms keep was reducing as time increases. Do you understand? All right. Please, do we understand? Who is in the house? Grace, Maria Bright, Jessica, are we there? Are we there? Do we understand? Oh, this is my diagram. It's going this way. Let me draw it well. So this is 5 grams, okay? All right. Are we done? Okay, so let's move to the next one, which is decay constant. All right, I've answered this question before. E is beta particle. I've answered it long ago. E is beta particles. So let me proceed with decay constant. The symbol is this. Okay. Okay, please, I'm having network issues. I'm not seeing your messages coming up, okay? Okay, but I'm dividing by 4 because of the half-life, okay? I don't know why I'm not seeing your messages. So sorry. My network is fucking me up this time. The last one I can see here is Mario Okorafo. Okay, but why I'm dividing by 4? Like I told you, is that of half-life. Okay? that the half-life, if you have a mass of what, 20 grams, right? And this mass is the original number of atoms before decay. Now, it is assumed to be my NO, original number of atoms before decay, right? Okay, then let me assume again that the half-life is 4 years. After 4 years, this mass is going to decay to half of its original value because the half-life is 4 years. So I'm going to have N naught over 2. Do you understand? I'm going to have N naught over what? 2. So that is 20 divided by 2 to give me what? 10 grams. Then after another 4 years, I'm still going to have, this is 4 years, right? I now have to divide this by 2 again. If I go this, I have N naught over 4. How do I get N naught over 4? So this is just like saying N naught over 2, that is this one, divided by what? 2, right? We'll bring it down to say N naught over 2 times 1 over 2, right? This will give rise to N naught over 4. That is what I have after the second half-life. So the value will now go down to what? 5 grams. Do you understand? So this is why I divided this by 4. As the time increases, the mass of the atom, the mass of the element will keep going down, and this will keep going down, and the time is increasing. Okay, all right. Oh, my network, I'm not seeing your messages again. I'm trying to see if I can't see again, and I don't know why. So sorry. Okay. Ah, God. Okay, Charity. So what I'm dividing is this one. I'm dividing this one by 2. Okay, that is half of its original. It will go down by 2. I'm dividing this by 2 and not by 4. Remember, if this is my N naught and I divide it, and I will get what? 10 grams. So here this becomes N naught over 2, which is my 10 grams. Okay, so if I divide this 10 grams again, I'm going to get 5. But coming to this place, my 10 grams is N naught over 2. So me dividing it again, I'm going to have N naught over 4, which is the same thing as what? 5 grams. Okay, that's what I mean. That's what I mean. Do you understand now? Dividing it again is what? N naught over 2 divided by 2, which will give rise to N naught over 4, which is what I have. So this is how the process continues until no element is remaining. No element is left, rather. Okay? All right. Okay. Okolafo, do you understand now? Don't know if I'm getting your network now. Okay, thank God I'm seeing it now. Ephraim George. Okay, now I can see all your questions. Thank God. Okay. Okay, Cole, have I answered your question? Sorry. I'm just seeing your messages now. The thing was hidden. I have to see how I can get it out so I can be answering your questions. Maria, let me go back to your question. Okay, Cho, you say, why am I dividing by 4? Have I answered that? Maria. Okay. This class is not for SS1, it's for SS3. So sorry. The thing was hidden. Okay. Maria, have I answered your question? Choni, what's the question, please? I'm just in your chat now. Okay, Maria, I understood, okay. Justina, yes, I used to do maths, but I've not started mathematics. I've not really started it like a life class. Okay, so Maria, we are good to go, okay? Thank God I was able to fix it. Okay, so do we understand? Okay, let me explain the decay constant on the board. Decay constant, the symbol is lambda, is defined as the instantaneous rate of decay per unit atom of what? Of a substance. Okay? So the magnitude, let me just put it down. That is change in the number of atoms is equals to minus lambda n. Okay, so this is the instantaneous rate of decay per unit atom, right? While lambda is the decay constant. So why do we have a negative sign here? The negative sign simplifies that the atom decreases as the time increases. You have seen it from half-life, that if given a certain time, an atom tends to do what? Tends to decrease. Do you understand? So the atom tends to do what? Tend to decrease. So that is that. Now we should know that, okay, let me say, where n is number of atoms after decay or disintegration. Okay, lambda is decay constant. Yt is what? Time. When we are using this formula to solve, we don't normally put negative sign. Negative sign implies that the atom tends to decrease, okay, based on half-life. It tends to reduce in its quantity, okay. The mass tends to reduce at a certain time. As the time increases, the mass of the number of atoms in that element tends to do what? Tends to decrease. That is why we have that negative sign here. All right. So I'm going to dive in the relationship between half-life and decay constant. Okay, Justina, you're here for the first time. Have you subscribed to the channel when I'm going to start doing maths? Okay. Justin, I will think about it when I'm going to start maths, but I'm going to start it very soon. Maybe to be on a weekend basis. Okay. You have subscribed to the channel, okay? Are you one of my students? Are you in Port Harcourt, Nigeria? Justina, are you in Port Harcourt, Nigeria? All right, are we done writing? So we can solve problems on decay constant and half-life. Okay, Justina, you are not. Okay, so can you chat me after now on my channel, so I will inform you when I want to start maths. Okay, I think that will be fine. Chat me after now, then when I'm ready for maths, I'm going to start mathematics. Is that okay? All right. Relationship between half-life and decay constant. So I have T half is equal to 0.693 over lambda, okay, or lambda is equal to 0.693 over half-life, right? Where T half is half-life and lambda is what? Decay constant. Okay, now this is the relationship between half-life and decay constant. Okay, so most times half-life does not have a specific unit. It can be in years, it can be in days, it can be in hours, depending on the nature of the question. Okay, so if decay constant is measured in per second, half-life is going to be in what? In seconds. So depending on the nature of the question, do we get it right? Okay, just now you're from Edo State, okay? So you can, like I said, you can chat me after now, then I will inform you. You're in which class? Okay, Maria, 0.693 is a constant anyway. It is gotten from a derivation of integral. It's a long derivation, so I don't know if you want me to start doing the derivation now. SS3, okay. Are you science or art, Justina? Science, okay, beautiful. So you can join our class, okay? For this weekend, from now till weekend, we'll be on teaching SS3 by 4, right? You can join us. Then you can chat me later after now, so I can tell you more about the maths. Okay? All right. Are we done writing? Are we done writing? Okay, we are done. Maria, you are done. Okay, so let's proceed. Can we look at the question on the board? All right. Now let's solve. A radioactive element has a decay constant of 0.077 per second. What is the half-life? Calculate the half-life. Okay? Now, from this question, just simple, we have that the K constant, lambda, is given as 0.077 per second, right? And you're asked to calculate the what? The half-life. Okay, there's a relationship between the half-life and decay constant, and that relationship is this: half-life is equal to 0.693 over lambda, right? And already, sorry for that, network was too bad. I'm going to divide my calculator to get 0.693 divided by 0.077. So my answer is going to give me what? 9 seconds. I don't know if you understand what I did. Okay, let me do a recap. A radioactive element has a decay constant of 0.077 per second. Calculate the half-life. And we are given the decay constant to be 0.077 per second. I have to calculate the half-life. The relationship between half-life and decay constant: half-life is equal to 0.693 over lambda. By the time we substitute it into what we have, our answer becomes 9 seconds. I hope you get it. Okay. Now, do we understand? Do you understand? All right. Okay, let's go to the next one. That will be example 2. Example 2. Radioactive element has a decay constant okay, let me change the question, but similar to what I have before. Let me change it. The half-life of a radioactive substance is 2 seconds. Calculate the decay constant. Okay. Now, can you try this? I'll give you a few minutes to look at it and send in your answers. Yes, victory. The 0.693 is a constant, okay? It's a constant. It was derived. Maybe in another class I'll be deriving it because we don't really have much time now. But then we use that constant to solve problems on decay constants and half-life. Are we solving? What's our answer, please? Please, if you are just joining, give it a thumbs up. What's our answer, please? All right. Ephraim George, your answer is, okay, Maria, your answer is 0.3465, okay? Ephraim George, 0.3465 per second, okay? Victor, you have 0.3465, okay? All right. Okay. Okay, so let's solve. Grace Kali, okay. Let's solve. Now, from the question, the half-life of a radioactive substance is 2 seconds. Calculate the decay constant. Okay. Now, from the question, my half-life is given as 2 seconds, right? I will ask to find the decay constant, which is what? Lambda. What do? We use our formula. You can say lambda is equal to 0.693 over half-life, okay? Which is equal to 0.693 over what? 2, because my half-life is 2. Then I divide to get 0.693 divided by 2. I'm going to have 0.3465. Now, since half-life is measured in seconds, in this question, unit of decay constant is going to be per what? Second. Is that clear? All right. Okay, so let's move to this question now. All right, now let's just dive into this question. Okay, a piece of radioactive material contains 10 power 20 atoms. If the half-life of the material is 20 seconds, the number of integrations in the first second is dash. Okay, let me go again. A piece of radioactive material contains 10 power 20 atoms. If the half-life of the material is 20 seconds, what is the number of disintegration in the first second? Now, for us to be able to solve this, you must remember that the number of disintegration, that is change in m over change in t, is equals to a negative, I tell you why you have negative, lambda what? M, right? This is the number of what? Disintegration that we are looking for. Okay? Now, we need to get the decay constant. Okay? Now, this is the number of atoms that it contains that they gave us, right? Now, what we need to do, the first thing for us to get the half-life is given as 20 seconds. Our half-life is given as 20 seconds. So let us get the decay constant. by saying decay constant is equals to 0.693 over half-life, right? So I will go by saying that decay constant is equal to 0.693 over my half-life is what? 20. So I'm going to divide by saying 0.693, okay, divide by 20, and my answer is equals to 0.03465, okay, per second. Now I've gotten that. For me to get the number of disintegration in the first second, now I'm going to multiply this decay constant with the number of atoms. And the number of atoms in the question is 10 power 20. All right? Now, I told you why we have this negative sign. Negative sign shows that the atom decays as the time increases. That is why it is negative. Now, with that being said, we just have to use our formula that the number of disintegration is equal to lambda times what? N. Now, what is my lambda? My lambda is what? 0.03465 times my n is 10 raised to power what? 20. Okay? So I'm going to multiply by saying 0.03465, okay, times exponent 20, right? So I'm going to have my answer to be 3.465 times 10 raised to the power of what? 18 per second. I don't know if you understand that. Do you understand what I explained? I said that the only option to this is the formula to use. But then, you're only giving the number of atoms, okay? But we don't know the number of disintegration. That's what you're looking for. So, the first thing we are giving the half-life. But we don't need half-life here, but we need decay constant. So, we're going to use this formula to get the decay constant, okay? Lambda is equal to 0.693 over half-life. If we substitute it inside by putting the half-life, which is 20, and I got 0.03465 per second, right? Then I'll put it here. I told you why we have the negative sign. It's because that the atom decreases as time progresses, all right? Now I'll have 0.03465 multiplied by what? My n is 20. I'll put my n is 10 raised to power 20, and I multiply, my answer becomes what? 3.465 times 10 raised to power 18 per second. Is that clear? All right. Okay, this is for SS3. Okay, this is for SS3. This is for SS3. Please, do we understand? Do we understand? We are coming to the end of this class. If you don't, you let me know. Let me explain so we can give assignments and call it a day. Yes, Ephraim Joe, that's the answer. That's the answer. Grace, you understood, okay? Okay, Carl, you understood, okay? Okay, are we done writing? I want to give assignment so we can close for today. We'll continue tomorrow. Okay. Okay, Bryce, you are done. Okay, so let's go to assignment. Okay, I'm coming. Let me get the assignment for you. Okay. All right. So let's do an end the class and continue tomorrow. All right. All right. This is your assignment for today. You can just copy it fast so we can go. Okay, so you can copy your assignment. We'll see tomorrow, same time, God's willing. All right, are we done? Are we done, please? We can call it a day. Are we done? Are we done? Copying, so we can go. Call it a day. Grace, you are done. Bright, Victory, Maria, Calio, you are done. All right. All right, thank you so much for staying to the end of the class. I believe we need to be able to understand a little bit on radioactivity. So tomorrow, same time, we are going to continue with some parts of radioactivity. See you next time in my next class. Bye. The time for SS2 tomorrow is by 11 SS2. Then SS3 is by 4. Okay? SS3 is by 4. All right. See you tomorrow. Bye for now.